Chapter 3. Induction and Exhaust Systems. Reciprocating Engine Induction Systems. The basic induction system of an aircraft reciprocating engine consists of an air scoop used to collect the inlet air, and ducting that transfers the air to the inlet filter. The air filter is generally housed in the carburetor heat box or other housing close by that is attached to the carburetor or fuel injection controller. The engine used in light aircraft is usually equipped with either a carburetor or a fuel injection system. After air passes through the fuel metering device, an intake manifold with long curved pipes or passages is used to send the fuel/air mixture to the cylinders. An induction air scoop is shown in Figure 3-1. The air scoop is located on the engine cowling to allow maximum airflow into the engine's induction system. The air filter, shown in Figure 3-2, prevents dirt and other foreign matter from entering the engine. Filtered air enters the fuel metering device, carburetor/fuel injector, where the throttle plate controls the amount of air flowing to the engine. The air coming out of the throttle is referred to as manifold pressure. This pressure is measured in inches of mercury, Hg, and controls engine power output. 3-1. Figure 3-1. Inlet scoop in engine cowling. Induction systems can consist of several different arrangements. Two that are used are the updraft and downdraft induction systems. An updraft induction system consists of two runners and a balance tube with intake pipes for each cylinder to deliver induction air to each cylinder's intake port. Figure 3-3. The balance tube is used to reduce pressure imbalances between the two-side induction runners. With carbureted engines, it is important to maintain a constant and even pressure in the induction system so that each cylinder receives equal amounts of fuel. On fuel-injected engines, the fuel is injected at the intake port just before the intake valve. It is important with this system to keep the pressure consistent at each intake port. A downdraft balanced induction system provides optimum airflow to each of the individual cylinders throughout a wide operational range. Figure 3-4. Better matched fuel-to-air ratios provide a much smoother and more efficient engine operation. Air from the induction manifold flows into the intake ports where it is mixed with fuel from the fuel nozzles, and then enters the cylinders as a combustible mixture as the intake valve opens. Basic carburetor induction system. Figure 3-2 is a diagram of an induction system used in an engine equipped with a carburetor. In this induction system, carburetor normal flow air is admitted at the lower front nose cowling below the propeller spinner, and is passed through an air filter into air ducts leading to the carburetor. A carburetor heat air valve is located below the carburetor for selecting an alternate warm air source, carburetor heat, to prevent carburetor icing. Figure 3-5. Carburetor icing occurs when the temperature is lowered in the throat of the carburetor, and enough moisture is present to freeze and block the flow of air to the engine. The carburetor heat valve admits air from the outside air scoop for normal operation, and it admits warm air from the engine compartment for operation during icing conditions. The carburetor heat is operated by a push-pull control in the cockpit. When the carburetor heat air door is closed, warm ducted air from around the exhaust is directed into the carburetor. This raises the intake air temperature. An alternate air door can be opened by engine suction if the normal route of airflow should be blocked by something. The valve is spring-loaded closed and is sucked open by the engine if needed. The carburetor air filter, shown in Figure 3-6, is installed in the air scoop in front of the carburetor air duct. Its purpose is carburetor air valve, carburetor, air filter, temperature bulb, warm air cold air, air intake duct, cold air actuator lever, drain line. Figure 3-2. Non-supercharged induction system using a carburetor. 3-2. Balanced crossover tube induction riser, hose clamp, throttle body, hose, induction risers, induction elbow. Figure 3-3. Updraft induction system, throttle body, intake manifold tube, hose, induction manifold assembly, intake manifold tube. Figure 3-5. Location of a carburetor heat air valve, intake gasket. Figure 3-4. Downdraft balanced induction system, to stop dust and other foreign matter from entering the engine through the carburetor. The screen consists of an aluminum alloy frame and a deeply crimped screen, arranged to present maximum screen area to the airstream. There are several types of air filters in use including paper, foam, and other types of filters. Most air filters require servicing at regular intervals, and the specific instructions for the type of filter must be followed. Figure 3-6. Figure 3-6. Location of air filter. 3-3. The carburetor air ducts consist of a fixed duct riveted to the nose cowling, and a flexible duct between the fixed duct and the carburetor air valve housing. The carburetor air ducts normally provide a passage for outside air to the carburetor. Air enters the system through the ram air intake. The intake opening is located in the slipstream, so the air is forced into the induction system giving a ram effect to the incoming airflow. The air passes through the air ducts to the carburetor. The carburetor meters the fuel in proportion to the air and mixes the air with the correct amount of fuel. The throttle plate of the carburetor can be controlled from the cockpit to regulate the flow of air, manifold pressure, and in this way, power output of the engine can be controlled. Although many newer aircraft are not so equipped, some engines are equipped with carburetor air temperature indicating systems which shows the temperature of the air at the carburetor inlet. If the bulb is located at the engine side of the carburetor, the system measures the temperature of the fuel/air mixture. Induction system icing. A short discussion concerning the formation and location of induction system ice is helpful, even though a technician's not normally concerned with operations that occur when the aircraft is in flight. Figure 3-7. Technicians should know something about induction system icing because of its effect on engine performance and troubleshooting. Even when an inspection shows that everything is in proper working order and the engine performs perfectly on the ground, induction system ice can cause an engine to act erratically and lose power in the air. Many engine troubles commonly attributed to other sources are actually caused by induction system icing. Induction system icing is an operating hazard, because it can cut off the flow of the fuel/air charge, or vary the fuel/air ratio. Ice can form in the induction system, while an aircraft is flying in clouds, fog, rain, sleet, snow, or even clear air that has high moisture content, high humidity. Induction system icing is generally classified in 3 types: impact ice, fuel evaporation ice, throttle ice. Chapter 2 discusses types of icing in more detail. Induction system ice can be prevented or eliminated by raising the temperature of the air that passes through the system, using a carburetor heat system located upstream near the induction system inlet and well ahead of the dangerous icing zones. This air is collected by ducts surrounding the exhaust manifold. Heat is usually obtained through a control valve that opens. Impact ice, throttle ice, fuel evaporation ice. Figure 3-7. Location of a carburetor heat air valve. The induction system to the warm air circulating in the engine compartment and around the exhaust manifold. Improper or careless use of carburetor heat can be just as dangerous as the most advanced stage of induction system ice. Increasing the temperature of the air causes it to expand and decrease in density. This action reduces the weight of the charge delivered to the cylinder, and causes a noticeable loss in power because of decreased volumetric efficiency. In addition, high intake air temperature may cause detonation and engine failure, especially during takeoff and high-power operation. Therefore, during all phases of engine operation, the carburetor temperature must afford the greatest protection against icing and detonation. When there is danger of induction system icing, the cockpit carburetor heat control is moved to the hot position. Throttle ice or any ice that restricts airflow or reduces manifold pressure can best be removed by using full carburetor heat. If the heat from the engine compartment is sufficient and the application has not been delayed, it is only a matter of a few minutes until the ice is cleared. 3-4. When there is no danger of icing, the heat control is normally kept in the cold position. It is best to leave the control in this position if there are particles of dry snow or ice in the air. The use of heat may melt the ice or snow, and the resulting moisture may collect and freeze on the walls of the induction system. To prevent damage to the heater valves in the case of backfire, carburetor heat should not be used while starting the engine. Also, during ground operation only enough carburetor heat should be used to give smooth engine operation. Part throttle operation can lead to icing in the throttle area. When the throttle is placed in a partly closed position, it, in effect, limits the amount of air available to the engine. When the aircraft is in a glide, a fixed-pitch propeller windmills, causing the engine to consume more air than it normally would at this same throttle setting, thus adding to the lack of air behind the throttle. The partly closed throttle, under these circumstances, establishes a much higher than normal air velocity past the throttle, and an extremely low pressure area is produced. The low pressure area lowers the temperature of the air surrounding the throttle valve. If the temperature in this air falls below freezing and moisture is present, ice forms on the throttles and nearby units restricting the airflow to the engine causing it to quit. Throttle ice may be minimized on engines equipped with controllable pitch propellers by the use of a higher than normal brake mean effective pressure, BMEP, at this low power. The high BMEP decreases the icing tendency, because a large throttle opening at low engine revolutions per minute, RPM, partially removes the temperature reducing obstruction that part throttle operation offers. Induction system filtering. Dust and dirt can be a serious source of trouble to an aircraft engine. Dust consists of small particles of hard, abrasive material that can be carried by the air and drawn into the engine cylinders. It can also collect on the fuel metering elements of the carburetor, upsetting the proper relation between airflow and fuel flow at all engine power settings. It acts on the cylinder walls by grinding down these surfaces and the piston rings. Then, it contaminates the oil and is carried through the engine, causing further wear on the bearings and gears. In extreme cases, an accumulation may clog an oil passage and cause oil starvation. Although dust conditions are most critical at ground level, continued operation under such conditions without engine protection results in extreme engine wear and can produce excessive oil consumption. When operation in a dusty atmosphere is necessary, the engine can be protected by an alternate induction system air inlet, which incorporates a dust filter. This type of air filter system normally consists of a filter element, a door, and an electrically operated actuator. When the filter system is operating, air is drawn through a louvered access panel that does not face directly into the airstream. With this entrance location, considerable dust is removed as the air is forced to turn and enter the duct. Since the dust particles are solid, they tend to continue in a straight line, and most of them are separated at this point. Those that are drawn into the louvers are easily removed by the filter. In flight, with air filters operating, consideration must be given to possible icing conditions which may occur from actual surface icing, or from freezing of the filter element after it becomes rain-soaked. Some installations have a spring-loaded filter door, which automatically opens when the filter is excessively restricted. This prevents the airflow from being cut off when the filter is clogged with ice or dirt. Other systems use an ice guard in the filtered air entrance. The ice guard consists of a coarse mesh screen located a short distance from the filtered air entrance. In this location, the screen is directly in the path of incoming air, so that the air must pass through or around the screen. When ice forms on the screen, the air, which has lost its heavy moisture particles, passes around the iced screen and into the filter element. The efficiency of any filter system depends upon proper maintenance and servicing. Periodic removal and cleaning of the filter element is essential to satisfactory engine protection. Induction system inspection and maintenance. The induction system should be checked for cracks and leaks during all regularly scheduled engine inspections. The units of the system should be checked for security of mounting. The system should be kept clean at all times, since pieces of rags or paper can restrict the airflow if allowed to enter the air intakes or ducts. Loose bolts and nuts can cause serious damage if they pass into the engine. On systems equipped with a carburetor air filter, the filter should be checked regularly. If it is dirty or does not have the proper oil film, the filter element should be removed and cleaned. After it has dried, it is usually immersed in a mixture of oil and rust preventive compound. The excess fluid should be allowed to drain off before the filter element is reinstalled. Paper-type filters should be inspected and replaced as needed. Induction system troubleshooting. Figure 3-8 provides a general guide to the most common induction system troubles. Supercharged induction systems. Since aircraft operate at altitudes where the air pressure is lower, it is useful to provide a system for compressing the fuel/air mixture. Some systems are used to normalize the air pressure entering the engine. These systems are used to regain the air pressure lost by the increase in altitude. This. 3-5. Probable cause isolation procedure correction. 1. Engine fails to start. Induction system obstructed. B. Air leaks. 2. Engine runs rough. A loose air duct. B. Leaking intake pipe. C. Engine valves sticking. D. Bent or worn valve push rods. 3. Low power. A restricted intake duct. B. Broken door in carburetor air valve. C. Dirty air filter. 4. Engine idles improperly. A shrunken intake packing. B. Hole in intake pipe. C. Loose carburetor mounting. Inspect air scoop and air ducts. Inspect carburetor mounting and intake pipes. Inspect air ducts. Inspect intake pipe packing nuts. Remove rocker arm cover and check valve action. Inspect push rods. Examine intake duct. Inspect air valve. Inspect air filter. Inspect packing for proper fit. Inspect intake pipe. Inspect mount bolts. Remove obstructions. Tighten carburetor and repair or replace intake pipe. Tighten air ducts. Tighten nuts. Lubricate and free sticking valves. Replace worn or damaged push rods. Remove restrictions. Replace air valve. Clear air filter. Replace packing. Replace defective intake pipes. Tighten mount bolts. Figure 3-8. Common problems for troubleshooting induction systems. Type of system is not a ground boost system, and it is not used to ever boost the manifold pressure above 30 inches of mercury. A true supercharged engine, called ground boosted engines, can boost the manifold pressure above 30 inches of mercury. In other words, a true supercharger boosts the manifold pressure above ambient pressure. Since many engines installed in light aircraft do not use any type of compressor or supercharging device, induction systems for reciprocating engines can be broadly classified as supercharged or non-supercharged. Figure 3-9. Supercharging systems used in reciprocating engine induction systems are normally classified as either internally driven or externally driven, turbo-supercharged. Internally driven superchargers compress the fuel/air mixture after it leaves the carburetor, while externally driven superchargers, turbochargers, compress the air before it is mixed with the metered fuel from the carburetor. Internally driven superchargers. Internally driven superchargers were used almost exclusively in high-horsepower radial reciprocating engines, and are engine-driven through a mechanical connection. Although their use is very limited, some are still used in cargo carriers and spray planes. Except for the construction and arrangement of the various types of superchargers, all induction systems with internally driven superchargers were very similar. Aircraft engines require the same air temperature control to produce good combustion in the engine cylinders. For example, the charge must be warm enough to ensure complete fuel vaporization and, thus, even distribution. At the same time, it must not be so hot that it produces volumetric efficiency, or causes detonation. All reciprocating engines must guard against intake air that is too hot. As with any type of supercharging, compressing intake air, the air gains heat as it is compressed. Sometimes this air requires cooling before it is routed to the engine's intake ports. With these requirements, most induction systems that use internally driven superchargers must include pressure and temperature sensing devices, and the necessary units required to warm or cool the air. The simple internally driven supercharger induction system is used to explain the location of units and the path of the air and fuel/air mixture. Figure 3-10. Air enters the system through the ram air intake. The intake opening is located so that the air is forced into the induction system, giving a ram effect caused by the aircraft moving through the air. The air passes through ducts to the carburetor. The carburetor meters the fuel in proportion to the air and mixes the air with the correct amount of fuel. The carburetor can be controlled from the cockpit to regulate the flow of air. In this way, the power output of the engine can be controlled. The manifold pressure gauge measures the pressure of the fuel/air mixture before it enters the cylinders. It is an indication of the performance that can be expected of the engine. The carburetor air temperature indicator measures either the temperature of the inlet air or of the fuel/air mixture. Either the air inlet or the mixture temperature indicator serves as a guide so that the temperature of the incoming charge may be kept within safe limits. If 3-6. Figure 3-9. An example of a naturally aspirated reciprocating engine. 30, 35, 25, 40. Manifold press. Intake pipe. 20, 15. In HG 10, 50, 45, 10, 20, 0, minus 10, 50. Carb. Temp. C degrees. Intake air duct. Manifold pressure. Carburetor heat valve. Carburetor air temperature bulb. Carburetor. Throttle valve. Supercharger. Figure 3-10. Internally driven supercharger induction system. The temperature of the incoming air at the entrance to the carburetor scoop is 100 degrees Fahrenheit. There is approximately a 50 degrees Fahrenheit drop in temperature because of the partial vaporization of the fuel at the carburetor discharge nozzle. Partial vaporization takes place and the air temperature falls due to absorption of the heat by vaporization. The final vaporization takes place as the mixture enters the cylinders where higher temperatures exist. The fuel, as atomized into the airstream. 3-7. That flows in the induction system, is in a globular form. The problem, then, becomes one of uniformly breaking up and distributing the fuel, remaining in globular form to the various cylinders. On engines equipped with a large number of cylinders, the uniform distribution of the mixture becomes a greater problem, especially at high engine speeds, when full advantage is taken of large air capacity. One method, used mainly on radial reciprocating engines, of improving fuel distribution is shown in figure 3-11. This device is known as a distribution impeller. The impeller is attached directly to the end of the rear shank of the crankshaft by bolts or studs. Since the impeller is attached to the end of the crankshaft and operates at the same speed, it does not materially boost or increase the pressure on the mixture flowing into the cylinders. But the fuel remaining in the globular form is broken up into finer particles as it strikes the impeller, thereby coming in contact with more air. This creates a more homogeneous mixture with a consequent improvement. Primer nozzle. Manifold pressure. 30, 35, 20. Manifold press. 25, 40, 15. In HG 45, 10, 50. Crankshaft. Ring type oil seal. Diffuser chamber. Tail shaft. Inlet. Counterweight. Large diameter impeller. Manifold ring. Slip joint. Rubber gasket. Gland nut. Figure 3-11. Location of a carb heat air valve. In distribution to the various cylinders, especially on acceleration of the engine, or when low temperatures prevail, to obtain greater pressure of the fuel/air mixture within the cylinders. The diffuser or blower section contains a high-speed impeller. Unlike the distribution impeller, which is connected directly to the crankshaft, the supercharger, or blower impeller, is driven through a gear train from the crankshaft. Turbo superchargers. Externally driven superchargers, turbo superchargers, are designed to deliver compressed air to the inlet of the carburetor or fuel/air control unit of an engine. Externally driven superchargers derive their power from the energy of engine exhaust gases directed against a turbine that drives an impeller that compresses the incoming air. For this reason, they are commonly called turbo superchargers or turbochargers. To be a true supercharger, it must boost the manifold pressure above 30 Hg. The typical turbo supercharger, shown in figure 3-12, is composed of three main parts. 1. Compressor assembly. 2. Turbine wheel assembly. 3. A full floating shaft bearing assembly. Detailed examples of a turbo supercharger are shown in figure 3-13. In addition to the major assemblies, there is a baffle between the compressor casing and the exhaust gas turbine that directs cooling air to the pump and bearing casing, and also shields the compressor from the heat radiated by the turbine. In installations where cooling air is limited, the baffle is replaced by a regular cooling shroud that receives its air directly from the induction system. The compressor assembly is made up of an impeller, a diffuser, and a casing. The air for the induction system enters through a circular opening in the center of the compressor casing, where it is picked up by the blades of the impeller, which gives it high velocity as it travels outward toward the diffuser. The diffuser vanes direct the airflow as it leaves the impeller, and also converts the high velocity of the air to high pressure. Motive power for the impeller is furnished through the impeller's attachment to the turbine wheel shaft of the exhaust gas turbine. This complete assembly is referred to as the rotor. The rotor revolves on the oil feed bearings. The exhaust gas turbine assembly consists of the turbocharger and wastegate valve. Figure 3-14. The turbine wheel, driven by exhaust gases, drives the impeller. The turbo housing collects and directs the exhaust gases onto the turbine wheel. And the 3-8. Center housing. Turbine housing. Turbine wheel assembly. Compressor wheel assembly. Compressor housing. Full floating shaft bearing assembly. Exhaust inlet, exhaust outlet, compressor inlet. Compressor outlet. Figure 3-12. A typical turbo supercharger and its main parts. Compressor housing. Compressor impeller, Center housing. Oil feed pressure bearing. Turbine. Turbine housing. Turbocharger components. Figure 3-13. Detail examples of the main components of a turbo supercharger. 3-9. Exhaust risers. Controller. Exhaust risers. Turbocharger 1-3-5. Turbocharger 2-4-6. Exhaust waste ticket valve. Tailpipe 2-4-6. Tailpipe 1-3-5. Figure 3-14. Exhaust gas turbine assembly. Wastegate regulates the amount of exhaust gases directed to the turbine. The wastegate controls the volume of the exhaust gas that is directed onto the turbine, and thereby regulates the speed of the rotor, turbine and impeller. Figure 3-15. If the wastegate is completely closed, all the exhaust gases are backed up and forced through the turbine wheel. If the wastegate is partially closed, a corresponding amount of exhaust gas is directed to the turbine. The exhaust gases, thus: butterfly, piston, oil outlet port controller, oil inlet port, seal, power cylinder drain port. Figure 3-15. Wastegate control of exhaust. 3-10.